Hello everyone, my name is Tej and today I will be presenting our project AI based multitask image enhancement using diffusion models and LORA fine tuning. The goal of our project is to build a unified system that can perform four different image enhancement tasks: colorization, in painting, denoising, and super resolution. Instead of building separate models for each task, we wanted a single platform that is powerful, scalable, and easy for non technical users to interact with. Our motivation came from real world needs. There are many areas such as old photo restoration, medical image pre processing, damaged image repair, and digital media enhancement, where traditional techniques either blur important details or fail to reconstruct missing information. Diffusion models have recently emerged as a state of the art solution because they generate images through an iterative denoising process, which naturally leads to realistic and detailed outputs. However, training full diffusion model is computationally very expensive. This is where LORA or low rank adaptation becomes extremely useful. Instead of fine tuning the entire stable diffusion model, LORA let us train only a small number of additional parameters. This reduces training cost by almost 95%, while still allowing the models to adapt effectively to new tasks like coloration and in painting. For deployment, we created an interactive Hugging Face space where users can upload an image, select the enhancement task, and instantly view the result. The backend uses a Flask API to route each request to the appropriate diffusion pipeline. This modular design allows us to keep the system lightweight and scalable. So overall, the vision behind this project is to combine the strength of modern diffusion models with practical deployment, making advanced image enhancement accessible to anyone with just a browser. Now let me talk about the dataset we used and why we selected it. For this project, we choose the COCO data set, the common object in context. COCO is one of the most widely used benchmark dataset in computer vision, and it contains a large variety of real-world scenes, objects, lighting conditions, people, and environments. There are three key reasons why Coco was the best choice for our project. First, the dataset is extremely diverse. Since tasks like colorations and in-painting require strong semantic understanding, such as knowing what color the sky should be or how texture should look on a wall, we needed a dataset that covers a wide range of everyday scenes. Coco provides exactly that. Second, Coco includes high quality segmentations, mask. This is especially important for in painting, where we need precise mask regions to simulate or damaged image portions. These masks allow us to generate realistic training samples where parts of the image are removed and the model learns to fill them in. Third, Cocoa is public, well benchmarked, and easy to pre-process. This allows us to resize image constantly to 512 into 512 and create grayscale, mask, and noisy version for each training task. Using a standardized dataset helps ensure that our results are reproducible and comparable to other systems. To give a quick overview of the dataset preparation, for the coloration model, we created pair of grayscale images and corresponding color images. For the in-painting model, we generated mask images where random regions were removed paired with the original image. For denoising, we added synthetic noise, a different level. And for super resolutions, we downsampled images to create low resolution inputs. We split each dataset into training, validation, and test sets following a clean structure. For example, 1050 training images and 225 each for validation and testing. This ensures that our evaluation was fair and that the model wasn't unintentionally memorizing the training data. The COCO dataset richness played a major role in enabling our diffusion models, especially the LORA fine-tuned versions to generalize well across different type of images. That concludes the introduction and dataset portion of our project. Next, we can move into the system architecture, model design, and results, where we will demonstrate the actual performance improvements from our LORA fine-tuned diffusion pipelines. Thank you, and over to next section.
Hey everyone, Dylan here. Wanted to demo the denoiser and super resolution fine tuning of the unit portion of the pipeline. So yeah, okay. Overall, this is the architecture that we're using. So we also decided to use the app.py to like host a endpoint for the app to be able to execute the denoiser and super resolution as well as in painting and colorize. So yeah, so this is how it works. We have our Google Colab training and fine tuning kind of area. So for denoise and super resolution, I did a full training of the UNet weights, and then pushed those weights back up into the model endpoint in Hugging Face, which has 100 gig space available. And then so we created a Gradio app.py file and hosted that in a Hugging Face space. That was super fun to do. And then that will pull from the models endpoint, which has the weights, and then we'll do the inference. So yeah, so this is how that looks if you're interested. And then yeah, the demo I will add at the end of this video to show you those two things. The super resolution takes quite a while, so yeah, I can show you the results for that on the slide. And yeah, so talking about the denoising performance, I trained the unit for 5 epochs because it was, mostly about getting the pipeline up and running, and I didn't want it to take too long or cost too much. But yeah, you can see the picture in the middle here is the SD 1.5 original model and that's what it generated. And on the right hand side is the fine-tuned unit model. And I mean, I think there's less noise, but you can definitely see there's some strange artifacts happening. And so I think there's some work to do in optimizing this pipeline and ironing out any kinks that may be there. And so, yeah, below you can see I created some metrics to be able to like quantify as best you can, like what the differences are between the images. And so you can look in the research paper as well for the definition of the PSNR, the SSIM, and the LPIPs. But here they show that the fine-tuned model performed better based on the metrics. However, visual inspection, there are some question marks about, why we're seeing what we're seeing. So another note on this one is that because the images are the same size, it's actually kind of a bit of an easier problem to solve. Whereas this is the config here for the 2 different pipelines that I did. And then for the super resolution, the sizes gets upscaled, the image gets upscaled, so then it's harder to compare pixels because they're in different positions. You could downsample it and then compare, but I figured that was like also going to show differences, that even if the fine-tuned one was better, it would still show it is worse in the metrics, or it'd be different. And so, the original is not a great thing to compare against, pixel for pixel, basically. So I chose like a more visual approach for this one, and future work we can work on like better metrics to quantify this one. But yeah, this is the result. Again, it's not as blurry or blocky as the original kind of upscaled it to. So it is a kind of filling in some detail, but on the other hand, it's also like removing a whole bunch of detail that I don't think it should. So again, I think it needs some further fine-tuning and ironing out of the kinks maybe. But yeah, the takeaway is that we have the training loop, I have the inference, I have the ability to host it, and repeat this as many times as needed. I even have the ability to run this locally as well, so like cost-wise it's pretty good to do that. But yeah, it's not too expensive. And these are some of the improvements that we can go through to help improve the pipeline. Yeah, pretty standard stuff. I think debugging and just maybe also bringing in like an expert, someone who's very versed in this pipeline kind of idea to help suggest any improvements and stuff like that. So that would be the next step here. Yeah, thanks. I just finished the presentation and I wanted to demo the denoiser in the Super Resolution app. And these videos will follow from this point. Thanks. Say noisy tensor 0 to 1 and we denoise. And this should take some time. And it should kind of give you an indication here. There we go. So yeah, there we go. So doing just a few steps, because otherwise it takes forever. And yeah, that's the result. Not exactly the result I was expecting, but it's doing something, and it's returning an image that is there. So yeah, next steps would be to keep iterating on this and improve this result, increase the number of steps, longer epoch training, debug any issues with the pipeline as well. But yeah, the pipeline so far is, run the notebook, load the data set, do the training, save the unit, fine-tuned weights to the models on the Hugging Face model space, and then run the app, and then see the results. We also have metrics, but you can see that in the presentation as well. Cool, thank you. Hey everyone, so I wanted to show the super resolution. So this will take the low res version and blow it up into the full 4x. So yeah, you can see the logs. This is just a callback in the pipeline to indicate progress, and that's pretty fast. Yeah, and so you can see this is the kind of similar result to the slides. Does seem to blow it up, obviously, but also doesn't seem to be as blocky as the standard diffuser pipeline is. But definitely some room for adding back the details that were in the original, as you can see. But I'm not sure if this is a function of training or some other kind of kink in the pipeline. But yeah, I mean it's repeatable and can iterate on this. So yeah, overall I'm pretty happy with where we are, and yeah, some future improvements should be great. Oh, and this is running on quite a big GPU right now. So it's an 8V CPU with 30 gigs of RAM and 24 G RAM. Some of the smaller ones I had trouble getting it to load and run. But yeah, that's that. Cool. Thank you, everyone.
Hello, everyone. This is Darren, and I'm going to go over the colorizer and in painting on our application. We can select colorize, and this is going to take any grayscale image and convert it to a colored version. And we're just going to click run. It looks like it's not hanging on to the original image structure, which will still need adjustments in the parameters. We're also going to check in painting out. So in painting, I'm going to close this image. We can upload an image with a mask. For this application, the mask must be painted and filled with the true green color. And there you see it's infilled the area in green. And this is a good example because this box is same color, but it didn't modify that. For colorizer, the MSE loss, PSNR, SSIM, and FID were measured during training and on the test set. The loss basically going to be the pixel difference to the true image from the predicted PSNR is going to be the peak signal to noise ratio. We want this number to be the highest possible number. A higher number is going to represent more quality than noise. SSIM, structural similarity, we want a value of 1, which is going to be perfect structure similarity to the true image. And the FID for Shea inception distance, we want a 0, which would represent the feature distributions of the generated images matching the true images. You can see during training, a lot of them for the colorizer kind of leveled off, which is not what we want to see. That could also be why it The performance values are similar to the test set. So some adjustments to the data set and training will definitely be recommended. We end up using the stable diffusion version 1.5 model using the stable diffusion image to image pipeline that is going to let us compare the black and white image and the prompt, which is here to generate the color image. A lot of these adjustments to the parameters were needed to get color into the image and not too much color added so that it doesn't represent the original image. Increase strength, increase guidance scale, adjusting those parameters was able to get some color. Again, something that still needs to improve. This also was not trained on cartoon images, so adding a cartoon data set would definitely help. Examples of the test set that you have the true color image, the original image from the COCO data set, the base model, and similar performance with the fine-tuned model. You can see it's doing pretty well at colorizing these images here, but not preserving the original image. It's creating like a vehicle here. You're able to get some color, decent performance while adjusting parameters to conserve the structures in the cartoon image, even though it wasn't trained on it. For the end painting, one crucial adjustment that need to be made during pre-processing is making sure it uses a white mask image as reference when you are using the model. Otherwise, it would not get rid of your mask if it was black. So you could see here, this is after using the model with a black mask. Using a white mask, you're able to get the infilled areas for where the mask was. And here was some performance metrics during training on the train and validation sets. Peak signal to noise ratio, we want that to go as high as possible. So it does kind of jump up and then levels off around 4 epochs. And then the SSIM, we actually want that at 1. So it is starting to rise, but also leveling off. So that's not what we want. We'll have to adjust the training to improve this. I actually increased the lower rank on this to get a higher percentage of parameters during training. So that might be why we do see a little bit better performance increase on these than the colorizer. Typically, you're training about 1% using LoRa. We used 10 epochs for both batch of 2. This was the stable diffusion and painting model. Some artifacts in both is obviously not what we want, but the people did pretty good. You could see the person sitting becomes this person standing, pretty realistic for a small model. Some artifacts in this one at night, and then the dog. The structure seems good, and it added some spots even. Some future suggestions, including more images for fine-tuning the unit, add image augmentation, further hyperparameter tuning, even adjusting the prompt had a big impact in getting better quality images. Increasing the lower rank, so I only had 0.5%. We could get that definitely higher. Larger models using ControlNet can also influence how the pipeline behaves, so it could definitely help. I've seen some examples on Hugging Face. Could use some generated captions to have more accurate dynamic prompts. BAE might have a strong influence on the output more than the unit. So yeah, I think we'd have to look into that and how we're fine-tuning the model to get even better performance and more effective training. And then lastly, here's our contributions. Thank you, everyone.